Hi, and welcome to the world of instrumentation and control. Today is the 21st of December, 2023, and as you can see, Christmas is just around the corner. But we're not going to be talking about Christmas today. Instead, we're going to talk about something a little more interesting: thermocouples. The thermocouple is the simplest temperature sensor in terms of construction, and that's because a thermocouple is only made of two metal wires. The secret behind the thermocouple, however, is that those two wires are made of different metals. Any two wires that are made of different metals can be used as a thermocouple. All you have to do is join the two wires together at one end, and you have a thermocouple. Next, you just measure the voltage at the other end, and you can use that voltage to determine the temperature at the junction of the two wires. However, as is often true in life, things that look simple actually have something that complicates them. The principle by which the thermocouple works is called the Seebeck effect. It was discovered in 1822 by this guy, Thomas Johann Seebeck, a German physicist. Mr. Seebeck found that when you joined two wires of different metals together at the ends and subjected one junction to heat, the needle of a compass that was in close proximity deflected, indicating that there was a magnetic field around the wires. That magnetic field was produced by current flowing through the wires due to a voltage being generated when heat was applied to one of the junctions. Now, it would have been very convenient if the voltage was dependent only on the temperature of the hot junction. If that were the case, you would only need to convert the voltage to temperature. But sadly, that's not how it works. The voltage is dependent on the temperature difference between the hot and cold junctions. Therefore, in order to determine the temperature of the hot junction, which is the temperature we want to measure, you need to know the voltage and the temperature of the cold junction. Over the years, scientists and engineers have measured the equivalent voltage for each value of temperature difference, and they created temperature versus voltage tables for each type of thermocouple. So if you measure the voltage of the thermocouple and the temperature of the cold junction, you can determine the temperature at the hot junction using those tables. So how can you know the temperature of the cold junction? One thing you can do is to keep the cold junction at a temperature of 0 degrees Celsius. I've seen a lot of illustrations where the cold junction is immersed in an ice bath, which keeps the junction at a temperature of 0 degrees Celsius. Since you now know the voltage and the temperature of the cold junction, you can determine the temperature at the hot junction using the temperature versus voltage tables. Of course, it's not practical to build an instrument that has a built-in ice bath, and it's slightly less practical to build an instrument that has a built-in refrigerator that would keep the cold junction at a temperature of 0 degrees Celsius. A more sensible approach would be to measure the temperature of the cold junction and, with the voltage measurement, calculate the temperature of the hot junction using the aforementioned temperature versus voltage tables. This is how the majority of thermocouple type temperature measuring instruments are designed. Okay, let's talk about the nomenclature of thermocouples. I've been calling the junctions as the hot junction and the cold junction. I'm not sure why they're called that, but it may be because the thermocouple is mostly used to measure hot temperatures. That means the heat is applied to the hot junction, making it hotter than the cold junction. But this is not always the case. If you're measuring cold temperatures, it's possible that the hot junction will be colder than the cold junction. For this reason, the hot junction is now often referred to as the measuring junction, and the cold junction is referred to as the reference junction. Since there are many different types of metals and metal alloys, it follows that there can be more than 100 types of thermocouples. However, not all metals are suitable for use in thermocouples. For this reason, there are only 8 major types of thermocouples in use today. Note, however, that some manufacturers may create their own types, so it's important to properly identify what type you're using and its characteristics. So let's discuss the different types of thermocouples, starting from the top. Type J is made of iron and constantan, an alloy of copper and nickel. These metals are very common and makes this type one of the cheapest among all the thermocouples. Iron, however, oxidizes easily, especially in high temperatures and in oxygen-rich environments. Consequently, this type of thermocouple doesn't last very long. Type T is made of copper and constantan, metals that are also susceptible to corrosion. It is one of the most accurate, but has the lowest temperature range of all the thermocouples. Type K is the most popular choice for a thermocouple, mostly because it is quite cheap. But more than that, it has a wide temperature range and is more durable than type T, J, or E. Type E has the highest output voltage among all the thermocouples. It is more accurate than either type J, K, or N, but has a lower temperature range. Type N is very similar to type K in terms of temperature range and accuracy, but the materials it is made of makes it more durable, but a little more expensive. Types B, R, and S are mostly made of platinum, which is one of the most expensive metals in the world, so these types are almost as costly as RTDs. This metal, however, gives them the highest temperature limits of all the thermocouples. Type B has the best accuracy at temperatures above 800 degrees Celsius, but cannot be used at temperatures below 50 degrees Celsius. So it's very important that you know the characteristics of each type of thermocouple so that you can decide which one can be used with your application. Thermocouples cannot be used as bare wire sensors. They are metal wires after all, and that means they need protection. Thermocouples are usually inserted into an insulating tube, which serves 2 purposes. They make sure that heat only reaches the measuring junction and keeps the rest of the wires cooler. The insulating tube also serves to keep the wires from touching each other. If the wires were to touch, it will create an unwanted junction. The effect of an unwanted junction is that the measuring junction will become invisible to the measuring instrument, and the voltage as well as the temperature being measured will come from the unwanted junction instead of the measuring junction. Normally, thermocouples are inserted into a protective sheath. This sheath can be made from metal, such as stainless steel, or from a ceramic material if the temperatures being measured is higher than what metal sheaths can handle. Metal sheaths, however, do have an advantage versus ceramic sheaths. Thermocouples that do not touch the metal sheath wall are called ungrounded junction thermocouples. Aside from protecting the thermocouple from excessive temperatures and external forces, the metal sheath also provides protection from electrical interference, something that ceramic sheaths cannot provide. That protection, however, has a disadvantage. Since the heat has to pass through the sheath wall and through the intervening space between the sheath and the measuring junction, the ungrounded junction has a slow response. Another type of junction is the grounded junction. This is where the measuring junction is allowed to touch the wall of the metal sheath. Since the intervening space has been eliminated, this type of junction has a faster response than the ungrounded junction. The disadvantage is that the thermocouple has less protection from electrical interference. The last type of junction is the exposed junction. This is a thermocouple that is unprotected by any type of sheath. It has the fastest response to temperature, but has the poorest resistance to electrical interference. Obviously, the lack of a sheath also means that the thermocouple is unprotected from high temperatures and from gases that may cause the wires to corrode or deteriorate. These types are usually limited to measuring low temperatures or for general temperature measurements. Another piece of information that's good to know is that the temperature range of thermocouples are also dependent on the thickness of the wires. Generally speaking, thermocouples with thicker wires have a higher temperature range than those with thinner wires. Next, let's compare the characteristics of RTDs and thermocouples. As can be seen from the comparison table, thermocouples are cheaper, have a wider temperature range, have faster response times, and are more robust than RTDs. Remember, however, that type B, R, and S thermocouples are made of the same materials as RTDs, so the price comparison between these types of thermocouples versus RTDs is less. With regards to speed of response, even if the thermocouple slows down when inserted into a sheath, remember that RTDs are also inserted into sheaths, so their response times are both slowed down, but the thermocouple is still faster than the RTD. If you are after accuracy, however, RTDs are the best choice for temperature measurement. And that's it for thermocouples in this episode of the World of Instrumentation and Control. Next time, we'll talk about something a little bit more advanced than the topics of the previous videos. I'll be making a series of videos about PID, or proportional, integral, and derivative control. I think you'll find those videos interesting. I'll see you then.